Hi, welcome to Engineering Mechanics. My name is Arun Srinivasa and I am a professor of mechanical engineering at Texas A&M. Today we are going to talk about some things that you know intellectually, but it is very hard for you to realize that in fact that is how it happens. These things that you know intellectually but not realize it actually cause you lots of problems, and I'm hoping that with this very short video with some demo I can show you that these kinds of things are actually not something that you just take it from me, but it's really actually happens. So let's start. The first idea that we have is that force causes motion. And in reality, that's not how it works. Bodies can move without a force. But you need a force to change either the speed of motion or the direction of motion. That is, you need the force to change the velocity. So let's show that with a particular example, and then we will go from there. Okay, here's a body, which you can see that there's a small green arrow on that body. And what that means is that's the velocity it has. And when I run it, you will see that it goes equal distances in equal intervals of time, and therefore the body moves with a constant velocity. And you don't require any force for it. There you go. It's moving. You can see that I have like strobed it, so you can see that it is actually moving equal distances in equal intervals of time. Speed is constant, direction is constant. For this, you don't need any force. Very good. Now, they will cause translational acceleration vector. I will show you what I mean. A given force causes the center of mass to accelerate in the direction of the net force. It will cause the center of mass to accelerate in the direction of the net force. And the acceleration of the center of mass is the same no matter where the force acts on the body. So let's see what we mean by that. So let's go to our simulator and we'll see. Right now I have these forces, so you can watch this. I will turn on the simulator. There you go. Notice how the two forces together are causing the body to accelerate. Can you see that the distances are increasing continuously? So if I play that, you will see 1, 2, 3, you can see. Can you see that how the distances are increasing? That means it's accelerating. The green vector is the velocity, the blue vector is the acceleration, and notice that they are both in the same direction. Okay, so now let's see what happens if I apply the force somewhere else. So I'm going to apply the force not at this location, but at some other location. So let's change the location for a second. I'm going to go up here. I'm going to change the location of this force. Instead of acting at the center of the body, I'm going to make it act a little bit off. So first thing I want you to notice is that the center of this rectangle moves exactly the same way, but the rectangle itself will do bizarre things. Watch now. Look. Can you see? It's still, the center of the rectangle is going the same way. Can you see the velocity and acceleration are the same like the previous time? But the rectangle itself is doing some weird stuff. So the point is, the center of the rectangle, if you want to make it move and accelerate in a particular way, you can apply forces anywhere you like. Rest of the rectangle may do strange things. The center of the rectangle will do exactly this. The other point I want to make is the following. I want to show you that it is not it looks like it moves in the direction of the force. That's not really the case. I will set an initial velocity for this. Notice now initial velocity is not 0. So off you go. And now you can see that it's not even moving in a straight line. Can you see? It's going in a parabolic shape. So please remember, force does not make an object move. Force changes either the speed of motion or the direction of motion. So it has secondary effect. Okay, so that's item number 1. Item number 2 is that if I apply the force somewhere else, So let's take this force and apply it somewhere else. And you will see that it has a very interesting feature. There, I've applied this force somewhere else. Now you will see that depending upon where it's applied, it will not only change the velocity of the center of mass, but it will also change the rate at which it rotates around the center of mass. So this is a secondary action. So now you can see it's rotating. Can you see that? Look at that. And that has to do with the fact that the force was not where it used to act. So notice two effects. What are the two effects? One is translation like before. That's shown by the red and green, blue and green arrows. And then on top of it is a rotation. If I move the force, how much it rotates, how quickly it rotates, all these things will change. So, forces also cause bodies to change their rotational speed or axis of rotation, or both, around the center of mass. How much a force affects the rotational motion of the body depends upon where they act, unlike the case of translational motion. Remember, the way the force affects translational motion does not depend upon where it acts, as long as it acts on the body. Rotational motion, on the other hand, depends upon where it acts. Now we come to the next really puzzling thing, which is this. It is possible to arrange groups of forces in such a way that they have no effect on the acceleration of the mass. So if I arrange the groups, a group of forces like this, can you see that the forces will cancel out, so that there will be no net force on the body, so it will have no effect on the acceleration, no effect on the velocity. But they can affect the rotational speed or direction of the axis of rotation. The thing is, they are not all acting here, so together they will cause the body to either speed up or slow down how quickly it's spinning. So let's see that. So let's look at a situation. Now here, see, can you see I have two forces acting on this body. Is it obvious to you that the sum of the forces are zero because the forces are equal and opposite? So it will have no effect on the velocity of the body at all. But because they are not acting exactly at the center of mass, they still have effect on the rotational motion only. So you will see that this one will rotate only about its center of mass. Can you see the center of mass is not going anywhere, but the body is just rotating. Right? So you will see that the rate at which it rotates changes because of the way in which the forces are acting. Okay. Okay. But the most non-intuitive thing about this is the next step. By the way, these things are called concentrated moments, and the way we draw them is that we draw them like this. Instead of drawing all this stuff, oops, instead of drawing all this stuff, instead of drawing like this, we will just draw it like that. The rotational effect of this is drawn like this. This is called a concentrated moment, or in many cases it's called a couple because you need groups of forces. Okay? So now the most non-intuitive idea is this. If it is a pure or concentrated moment, its effect is the same no matter where the moment acts. It doesn't matter where it is. In other words, concentrated moments are to rotation what forces are to translation. So how does this work? Let's see with our example. So now first let's run this again so that you are sure about what happens. So here's a concentrated moment, and you can see it's starting to spin around its center of mass. I can show you that I'll get identical effect by moving this collection. So what I'm going to do is I'm going to deliberately stop this. I'm going to move it somewhere else. So let's move these forces to some other location. I'm going to go up here, move this to a different location. I'm going to put 0.6. So I'm going to move this. Same gap distance, everything is the same. I'm just going to move this to 0.2. Notice the whole thing has shifted to the side. Right? So now we will run this and you will see that it will have exactly the same effect. Watch. See? Exactly the same effect as before. Can you see? It's still rotating around its center of mass, even though the forces are not acting exactly around the center of mass. The reason is the torque from these couples has the same effect no matter where it acts. Just like forces have the same effect no matter where they act and the translational motion, torques have the same effect no matter where they act and the rotational motion. Thank you very much.